HADES, the Haiku Autonomous Defensive Exploitation System, is a predictive AI and machine learning cyber risk engine designed to show how advanced nation-sponsored threat actors could move through an environment before an attack occurs. The platform begins by creating a digital twin of the network. Instead of requiring teams to manually build their environment from scratch, HADES can ingest existing data from multiple sources, including Nessus and ACAS scans, Kubernetes and Terraform infrastructure, zip files, YAML configurations, scripts, and HADES network files. From that data, HADES builds a simulation of the environment. Devices, services, vulnerabilities, credentials, users, connections, cloud assets, network segments, and operational dependencies become part of a unified graph. HADES also includes the human layer. Personnel can be modeled with roles, departments, schedules, routines, access permissions, MFA status, administrative privileges, security awareness scores, and device relationships. This is critical because real attackers target people, credentials, workflows, and trust relationships. The platform includes threat actor profiles designed to represent different nation-sponsored and advanced persistent threat behaviors. These actors have distinct objectives, preferred techniques, targeting priorities, lateral movement patterns, and operational tendencies. For example, one actor may prioritize credential theft, social engineering, high-value personnel, and lateral movement. Another may focus on destructive operations, cloud compromise, satellite-linked infrastructure, command systems, or drone-related systems. HADES models those differences so teams can understand how different adversaries would behave inside the same environment. The system then simulates attack pathways across the digital twin. Using graph-based intelligence, HADES identifies likely entry points, high-value targets, exposed services, credential relationships, and possible pivot paths. It ranks attack paths based on probability, actor behavior, target criticality, technique alignment, and mission impact. HADES helps find the most likely path for a specific adversary by simulating how an actor could enter, move laterally, escalate privileges, compromise systems, trigger detections, encounter defensive controls, and attempt to reach its objectives. Each simulation produces a step-by-step attack sequence for review. Modeling defender visibility, HADES can show where EDR, H.A.D.E.S, CM coverage, patch posture, segmentation, MFA, and human security controls helped or failed to reduce risk. For control gap analysis, HADES identifies the specific defensive gaps that contributed to the simulated attack path. These may include missing endpoint detection, weak MFA, exposed services, insufficient segmentation, vulnerable credentials, or personnel with excessive privilege. The result is a prioritized set of remediation actions tied directly to simulated adversary behavior. This is what makes HADES different from traditional scanning tools. It shows what an adversary is likely to do with present vulnerabilities. For executives and commanders, it helps identify which actions are most likely to reduce mission risk, what requires immediate attention, and which threat actors are most relevant. HADES also uses multi-episode simulation and machine learning training. Teams can run repeated simulations against the same network to identify the most common attack paths, highest risk devices, most frequently used techniques, and recurring control gaps. This produces a higher confidence view of risk because the platform is not relying on a single path or a single outcome. It can evaluate how threat behavior changes across repeated runs and how effective the environment is at detecting, blocking, or recovering from attacks. HADES can operate offline and air-gapped, with vulnerability intelligence, CV data, exploit references, MITRE mappings, model training, simulation, and analysis running inside the local environment. HADES can model unmanned systems, UAV fleets, operators, command links, flight paths, autonomy levels, payload characteristics, communication ranges, jamming exposure, endurance, battery behavior, and environmental factors such as wind, terrain, altitude, and temperature. This enables teams to evaluate how cyber compromise could affect drone operations. HADES can model whether a drone depends on a human operator, if that operator is available, if the drone can complete a route, whether communication links are exposed, and whether electronic warfare or GPS spoofing could affect mission performance. HADES shows how compromise in the network could create operational consequences in the physical environment and in orbit. HADES can model satellite assets, orbital visibility, satellite passes, ground station relationships, communication pathways, protocol behavior, and space-to-ground dependencies. It supports satellite catalog integration and allows teams to evaluate when satellite assets are visible, reachable, or connected to mission systems. This allows teams to understand how satellite communications, ground terminals, and connected systems could become part of a broader attack path. Together, the cyber, drone, and satellite pillars give HADES a unified view of modern defense risk. Model the environment. Simulate the adversary. Prioritize the risk. Defend before impact.